There is a photograph, if you can call it that, taken by a telescope 1,000,000 miles from where you are sitting right now, that should not exist. It shows a galaxy. Not a smudge, not a hint, not a statistical whisper buried in noise, but a fully formed, rotating, star-populated galaxy, glowing with the light of hundreds of millions of suns. And when astronomers measured the light stretching away from it, the redshift, the fingerprint that tells us how far back in time we are looking, the number that came back made several of them, by their own account, check their equipment. Then check it again. The galaxy was there when the universe was a few 100 million years old, a cosmic infant. And yet it looked like it had already lived a long and complicated life. That single image and the dozens like it that followed, it opened a crack in one of the most successful scientific theories ever constructed. The story of how the universe began, how it aged, and how everything in it, including the atoms in your body, came to be. For almost a century, that story has held up against every test we could throw at it. It survived new instruments, new mathematics, new generations of skeptical scientists trying to break it. And it kept surviving. But now, for the first time in a long time, a very small number tucked inside a very large telescope's data is asking a very large question. What if we have the age of the universe wrong? Not off by a rounding error, not off by 1% or 2%, the way scientific estimates usually get refined over time. What if the number is wrong by billions of years? I want to walk you through how we got here, how astronomers built a timeline of the entire cosmos, tested it 1,000 different ways, they trusted it completely, and are now staring at evidence that either breaks it or forces something new and strange to be added to it. This is a story about galaxies that shouldn't be able to exist yet. About a mismatch in the expansion of space that has resisted a decade of explanations. About physicists proposing that the light from the dawn of time has been trying to tell us something we weren't ready to hear. By the end, I don't think you'll look at the night sky quite the same way. Because what's at stake isn't just a number. It's the story of where everything came from, and whether that story, the one we've told ourselves with such confidence, is actually complete. Let me start at the beginning. Or rather, let me start with how we ever figured out there was a beginning at all. For most of human history, the universe simply was. Eternal, static, unchanging, a backdrop against which human events played out, but not itself a subject of history. Aristotle thought the heavens were fixed and perfect. Newton, brilliant as he was, assumed an infinite, unchanging cosmos. And when his own equations hinted that gravity should cause such a universe to collapse in on itself, he quietly patched the problem rather than question the premise. Even Einstein, when his general theory of relativity implied in 1917 that space itself should be expanding or contracting, he added a fudge factor, a cosmological constant, specifically to force his equations to describe a static universe. He wanted the universe to be still. The mathematics wanted it to move. The mathematics won. In the 1920s, an astronomer named Edwin Hubble, working with the largest telescope in the world at the time, made an observation that would unravel thousands of years of assumption. He looked at distant galaxies and noticed something peculiar about their light. It was redder than it should be. Not because the galaxies were red, but because their light had been stretched, shifted toward longer, redder wavelengths in a way that precisely matched what you'd expect if those galaxies were racing away from us. And the farther away a galaxy was, the faster it appeared to be receding. There is only one tidy explanation for a universe where everything is rushing away from everything else in every direction. Space itself is expanding. Not galaxies flying through static space like shrapnel from an explosion, but space itself stretching, carrying galaxies along for the ride, the way raisins in a rising loaf of bread move apart from each other as the dough itself expands. And if space is expanding now, then rewind the tape. Yesterday, everything was slightly closer together. A year ago, closer still. Go back far enough, and everything, all the matter, all the energy, all the space itself, converges toward a single, unimaginably dense, unimaginably hot point. That is the Big Bang. Not an explosion happening in space, but the beginning of space itself. This single insight did something remarkable. It turned the universe from a stage into a character. The cosmos now had a biography, a birth, a childhood, an adolescence in which the first stars ignited and the first galaxies assembled themselves out of swirling clouds of hydrogen and helium. A slow maturation over billions of years into the vast, structured, galaxy-filled universe we observe today. And once you accept that the universe has a history, the next question becomes irresistible. How old is it? This turns out to be one of the most important numbers in all of science. Get it right, and you can reconstruct with startling precision the entire sequence of cosmic events. When the first atoms formed, when the first stars lit up the darkness, when galaxies like our own Milky Way began to take shape. Get it wrong, and the whole timeline unravels. Every subsequent chapter of cosmic history would need to be rewritten. So how do you weigh something as vast as the universe, or clock something as old as time itself? The answer scientists arrived at is almost embarrassingly elegant. If you know how fast the universe is expanding right now, a number called the Hubble constant, named for the astronomer who first measured that galactic recession, you can essentially run the expansion backward, like rewinding a film, until everything converges to a single point. The rate of expansion, combined with a well-tested theory of gravity and the physics of hot, dense matter in the early universe, lets you calculate not just that there was a beginning, but when it happened. Decades of increasingly refined measurements, using increasingly sophisticated instruments, converged on a remarkably consistent answer. The universe is approximately 13. 8 billion years old. Not very old. Not billions of years, give or take a lot. 13.8 billion years with an uncertainty of only about 1%. For a number describing the birth of literally everything, that is a staggering degree of precision. This number didn't come from one measurement. It came from many wildly different lines of evidence, all pointing to the same figure. The afterglow of the Big Bang itself, a faint microwave hiss that fills every corner of the sky, called the cosmic microwave background, carries within its subtle temperature variations an extraordinarily detailed fingerprint of the early universe, one that pins down its age with exquisite precision. The oldest stars in our galaxy, aged using the physics of stellar nuclear fusion, top out at just under 13.8 billion years old, consistent with, but never older than, the age of the universe itself, exactly as you'd expect if stars can't be older than the cosmos that contains them. Radioactive elements, whose decay rates are as reliable as any clock in nature, tell a matching story. 3 independent methods, 3 different branches of physics. One answer. It's worth pausing on that first method because it's the most powerful of the 3, and it will matter again later in this story. The cosmic microwave background isn't just a faint, uniform hiss. When you map it across the entire sky in detail, as satellites like COBE, WMAP, and later Planck did with ever-increasing precision, you find that it's not perfectly uniform at all. It's covered in extremely faint temperature variations, differing by only a few parts in 100,000 arranged in a pattern of blotches and rings of a very particular characteristic size. Those patterns are not random. They're the fossilized remnant of sound waves, actual pressure waves, rippling through the hot plasma of the infant universe in the first 380,000 years after the Big Bang, before atoms had even formed and light could travel freely for the first time. The characteristic size of those ripples depends, in a precisely calculable way, on how old the universe was when the light finally broke free, on how much ordinary matter and dark energy it contains, and on how the universe has expanded in all the time since. Feed the measured pattern into that calculation, and the age of the universe falls out as a direct consequence. Not a guess, not an extrapolation, but a number pinned down by the geometry of frozen sound waves from the dawn of time. That is why cosmologists trust the 13.8 billion year figure as deeply as they do. It isn't one clever estimate, it's the single self-consistent answer that a very demanding, a very overdetermined puzzle happens to produce. For a long time, this felt like one of the great triumphs of modern cosmology, proof that human beings, using nothing but light, mathematics, and patient observation, could reconstruct the biography of the entire universe. And then, in the summer of 2022, a new telescope opened its eyes for the first time. The James Webb Space Telescope was built to do many things, but one of its central missions was to look farther back in cosmic time than any instrument before it, to catch the light from the very first galaxies, the pioneers that lit up the darkness after the Big Bang. Nobody expected this to be easy. The prevailing models predicted that galaxies at that early stage would be small, faint, disorganized, clumsy first drafts of the majestic spiral and elliptical galaxies we see today. Little more than dim smudges of newly formed stars, very still in the process of gathering themselves out of primordial gas. Within months of the telescope's first images being released, that expectation collapsed. Astronomer pointed Webb's infrared eyes into what looked, to the untrained observer, like an empty patch of sky, and let it stare for hours, gathering the faintest photons that had been traveling toward Earth for over 13 billion years. What came back stunned the community. Galaxies that should have been small, dim, and barely assembled instead appeared bright, massive, and in several cases surprisingly well organized, with visible structure, significant stellar mass, and light profiles suggesting populations of stars that had already been burning for hundreds of millions of years. One early set of candidate galaxies, drawing enormous attention when their analysis was published in 2023. They appeared to exist when the universe was less than 500 million years old, and yet seemed to carry the stellar mass of a galaxy like our own Milky Way, which took over 10 billion years to build up that much material. Researchers began, half-jokingly and half-seriously, calling them universe breakers, because if the measurements held up, they broke the standard model of how quickly galaxies are supposed to be able to form. Let's slow down and be precise about why this is such a problem, because the issue isn't simply, wow, that's a big galaxy. It's a timing problem, a question of whether there was enough time physically for nature to do what it appears to have done. Here is the accepted theory, the one that has worked for decades. After the Big Bang, the universe was a hot, nearly uniform soup of particles. As it expanded and cooled, tiny irregularities in the density of matter, ripples imprinted in that primordial soup, began to grow under the pull of gravity. Regions that were slightly denser than average pulled in more matter, becoming denser still in a slow self-reinforcing process. Over hundreds of millions of years, these growing clumps of matter, dominated by an invisible substance called dark matter. They formed gravitational scaffolding. Ordinary gas fell into that scaffolding, cooled, and eventually collapsed into the first stars. Those stars gathered into the first small galaxies. Those small galaxies slowly merged and grew over billions of years into the large, mature galaxies we see filling the sky today. The prediction that falls out of this theory is specific and testable. Galaxy growth should be gradual. A galaxy that formed only a few 100 million years after the Big Bang simply hasn't had time to accumulate a large mass of stars, because star formation itself takes time, and merging smaller galaxies into bigger ones takes time, and both processes are bounded by the raw age of the universe at that moment. There's a speed limit on cosmic growth built into the physics of gravity and star formation. And the observation, the actual data streaming back from Webb, appeared in a number of these early candidate galaxies to blow straight through that speed limit. So some of the objects looked like they had built up stellar populations that should have required a much longer runway of cosmic time than the standard timeline allows them to have had. That is the conflict at the heart of this mystery. Not an unusual object, not an outlier we can set aside. A pattern showing up across multiple independent surveys of galaxies that appear too big, too early, too fast. Here's the mini mystery inside the bigger one, and it's worth pausing on. How do you even know how far away, and therefore how far back in time, you're looking when you're staring at a point of light billions of light years away? You can't send a tape measure. What astronomers use instead is that same redshift phenomenon Hubble first noticed in the 1920s. Because the universe has been expanding for the entire time light from a distant galaxy has been traveling toward us. That light gets stretched, shifted toward longer, redder wavelengths, and the amount of stretching tells you both how far away the galaxy is and how long ago you're seeing it. High redshift means ancient light. It's an extraordinarily well-tested technique, but it's also precisely the technique whose interpretation is now, for the first time in a generation, it's being seriously questioned by a subset of researchers for reasons I'll get into shortly. So we have, on one hand, mounting observational evidence of impossibly early, impossibly massive galaxies. And on the other hand, we have a well-tested theoretical framework, decades old, confirmed by mountains of independent evidence that says such galaxies shouldn't be able to exist yet. Something has to give. Either our theory of galaxy formation is subtly, fundamentally wrong about how quickly structure can build in the early universe, or our tools for measuring cosmic distance and time, the redshift technique itself, are missing something important. Or, and this is the possibility that has generated the most excitement and the most controversy, our estimate of the age of the universe itself, that confident 13. 8 billion year figure built from 3 independent lines of evidence needs to be revisited. If you think that last option sounds like a stretch, replacing one of the best tested numbers in all of science because of a puzzling set of galaxy images, you're not alone. Most cosmologists think that's not where this is headed. But you should know that the scientists making that argument are not cranks working at the fringes. They are publishing in peer-reviewed journals, presenting at major conferences, and pointing to a second, completely independent problem in cosmology that had already been quietly destabilizing the field for almost a decade before Webb ever launched. Because it turns out the impossible early galaxies are not the only crack in the wall. For years before Webb ever launched, cosmologists had been quietly wrestling with a problem so persistent it earned its own name, the Hubble tension. Remember that number I mentioned earlier? the Hubble constant, the rate at which the universe is expanding right now, the key ingredient in calculating the age of the universe. There are two fundamentally different ways to measure it, and by all rights, they should agree. The first method looks backward, using the cosmic microwave background, that ancient afterglow of the Big Bang, and essentially predicts from the physics of the early universe what the expansion rate ought to be today. This method, refined over years by missions studying that primordial light in extraordinary detail, consistently returns a value of about 67 kilometers per second per megaparsec. In plain terms, for every additional 3.3 million light years of distance, the universe appears to be expanding about 67 kilometers per second faster. The second method looks forward from the here and now, building what's called a distance ladder, using nearby stars whose true brightness we understand precisely, calibrating outward to more distant stars, and then to exploding stars called supernovae, which are bright enough to be seen across enormous distances, to directly measure how fast galaxies at various distances are actually receding from us today. This method, refined over decades using some of the best telescopes ever built, consistently returns a noticeably higher number, around 73 kilometers per second per megaparsec, 67 versus 73. It might not sound like much, but in a field where measurements routinely agree to, within a percent or two of each other, a gap this size, persisting stubbornly across a decade of increasingly precise, increasingly independent measurements, is not noise. It is a genuine disagreement between two different ways of asking the same question, and nobody has been able to make it go away. This matters enormously for our story, because the age of the universe and the expansion rate are two sides of the same coin. If the universe is truly expanding faster than the early universe method predicts, then, depending on how you resolve the discrepancy, the universe could be somewhat younger than we think. Or, if the resolution runs in the other direction, somewhat older. Either way, the clean, confident, single-number story of a 13. 8-billion-year-old universe is sitting on top of an unresolved tension between two of its own best measurement techniques. For a while, most cosmologists treated the Hubble tension and the impossible early galaxies as separate puzzles, two loose threads in an otherwise sturdy sweater. But a small, vocal group of researchers began to ask an uncomfortable question: what if they're the same thread? What if the reason JWST is finding galaxies that look too massive, too structured, too soon after the Big Bang, and the reason two independent methods of measuring cosmic expansion refuse to agree is that our fundamental timeline of the universe is off, not by a rounding error. By something much larger, this is where the story escalates from puzzling anomaly to possible paradigm crisis, and it's worth sitting with the magnitude of what's being proposed. Because most attempts to explain the JWST galaxies stay well within the standard cosmological model. They tweak the efficiency of star formation. They invoke feedback processes. They look for measurement errors. But a smaller, bolder set of proposals goes further, arguing that the standard model itself, the one anchoring the universe's age at 13.8 billion years, needs to be replaced or substantially revised. The most striking of these arrived in 2023, when a physicist named Rajendra Gupta proposed a modified cosmological model combining two ideas that mainstream cosmology had largely set aside decades earlier. The notion that light might lose energy, and therefore redshift, simply by traveling vast distances through space, independent of cosmic expansion, an idea historically called tired light, and the notion that certain fundamental constants of nature, like the strength of gravity, might have drifted slowly over the history of the universe. A coupling constants hypothesis with roots going back to some of Paul Dirac's speculative work in the 1930s. Combining a version of these ideas with standard expansion, rather than replacing expansion outright, Gupta's model produced a startling result, an estimated universe age not of 13.8 billion years, but of roughly 26. 7 billion years, nearly double the accepted figure. Let that sit for a second. Not a correction, not a refinement. A near doubling of the age of everything. If a model like this were correct, it would resolve the impossible early galaxies problem almost effortlessly. Those massive structured galaxies wouldn't be impossible at all, because there would have been nearly twice as much time for them to form. It's an elegant solution to a stubborn problem. Elegant enough that it made international headlines within days of publication, with outlets running stories suggesting the universe might be twice as old as we thought. But elegant is not the same as correct. And this is where I have to be honest with you about how science actually works, as opposed to how it gets reported. A single striking paper, even a peer-reviewed one, is not the same as a scientific consensus. Extraordinary claims, and the universe is nearly twice as old as we thought, is about as extraordinary as claims get, require an extraordinary weight of evidence before the field accepts them. The tired light and varying constants model is genuinely interesting, genuinely worth taking seriously, and genuinely faces serious challenges of its own. Earlier versions of tired light cosmology, dating back to the 1920s and 30s, were largely abandoned because they failed to explain other well-confirmed observations, particularly the detailed structure of the cosmic microwave background and the way distant supernovae dim and brighten over time in a manner that only makes sense if space itself is expanding, not if light is simply losing energy as it travels. Any modern revival of these ideas has to explain everything the standard model already explains, not just the one thing it's currently struggling with. So where does that leave us? Not with an answer, with 4 live possibilities, each defended by working scientists, each with real evidence behind it, and none of them yet strong enough to have won the argument outright. I think this is actually the most honest and most exciting place a scientific mystery can be. Not we don't know anything, but we know enough to be certain something doesn't add up, and not yet enough to say exactly what. Let's walk through the real contenders, one at a time, because each one tells you something different about how the universe might actually work, and each one, if confirmed, would rewrite a different chapter of the cosmic story. The first explanation is the most conservative, and for that reason, it's the one most cosmologists currently favor. The galaxies aren't breaking any laws of physics. We simply underestimated how efficiently the early universe could turn gas into stars. In this view, the standard timeline of cosmic history stays intact. The universe is still 13.8 billion years old. Dark matter still builds its gravitational scaffolding on schedule. But the process of star formation inside the first galaxies was far more efficient and far less self-limiting than our models assumed. Normally, when a young galaxy forms stars too quickly, the newborn stars themselves push back. Their radiation and stellar winds, and eventually their explosive deaths as supernovae, blow surrounding gas away, acting like a thermostat that slows further star formation. But some researchers have proposed that in the very early universe, conditions were different enough, gas densities higher, cooling more efficient, that galaxies could burn through their fuel in rapid, feedback-free bursts, building up large stellar populations far faster than a modern galaxy could manage. It's a genuinely compelling idea, and simulations built around it have successfully reproduced galaxies with brightness and mass similar to what Webb is finding. Its weakness is that it requires star formation to behave in a way we've never directly observed, extrapolated from physics we understand well in other contexts, but have never tested under early universe conditions. It solves the puzzle by stretching a known process to its limits, rather than inventing something new, which is either a strength or a weakness, depending on how much you trust extrapolation. The second explanation takes a stranger route. What if the earliest galaxies aren't quite galaxies at all, but the light of enormous black holes, feasting on infalling gas so voraciously that they briefly outshine the combined light of every star in their host galaxy? This isn't as far-fetched as it sounds. We already know supermassive black holes exist at the centers of galaxies, including our own, and we know that actively feeding black holes, quasars, can be among the brightest objects in the universe. If a significant number of Webb's impossible galaxies actually derive much of their light from an unusually large population of these actively feeding black holes rather than from ordinary starlight, that would inflate our estimates of how much stellar mass and therefore how much star formation must have occurred without requiring galaxy formation itself to violate any timeline. Some follow-up observations have found tantalizing evidence supporting this for a subset of the most extreme objects, identifying signatures characteristic of black hole accretion rather than starlight, broad, smeared spectral lines, and unusual color patterns that better match hot gas swirling into a black hole than the steady glow of ordinary stars. Researchers have even coined a nickname for the smallest, most compact versions of these objects: little red dots, a population of surprisingly numerous, unexpectedly red, extremely compact sources that Webb turned up in far greater numbers than anyone anticipated, and that many researchers now suspect are dominated by actively feeding black holes rather than mature galaxies at all. That's a genuinely satisfying partial resolution. But, and this is important, it doesn't appear to account for all of the puzzling galaxies. A meaningful fraction still look, by every available diagnostic, like they're dominated by genuine, very mature starlight, which brings the mystery right back to the timing problem. The third explanation turns the telescope's data against itself, questioning not the universe, but our measurement of it. Determining a galaxy's redshift, and therefore its distance and age, from Webb's images isn't always done with a precise spectrum, a full rainbow breakdown of the galaxy's light. Often, for the faintest, most distant candidates, astronomers rely on a faster, cruder technique, comparing brightness across just a handful of broad color filters and inferring redshift from the pattern, a method called photometric redshift estimation. It's a well-tested technique, but it's also known to occasionally misfire, especially for unusual or dust-obscured objects, sometimes mistaking a closer, dustier, more ordinary galaxy for a much more distant, seemingly impossible one. When astronomers have gone back with more careful spectroscopic follow-up, the slower, more rigorous rainbow breakdown method, some of the most extreme universe breaker candidates have indeed turned out to be closer and therefore less anomalous than first reported. This is genuinely reassuring, and it has trimmed the size of the mystery. But, and every honest account of this story has to include this but, it has not eliminated it. A stubborn core of galaxies, confirmed with the more rigorous spectroscopic method, still appear to be too massive too soon, which brings us to the fourth explanation, the one we already met. that our fundamental timeline of the universe is the thing that's actually broken, whether through a revived and modified version of tired light cosmology, a genuinely evolving early dark energy component that briefly sped up cosmic expansion in the young universe before fading away, or some other modification to the standard model that nobody has proposed yet. This is the explanation with the highest ceiling. If true, it doesn't just resolve the galaxy puzzle. It resolves the Hubble tension too, killing two long-standing anomalies with one stone. And also the highest bar to clear, because it asks us to abandon or substantially revise a framework that has correctly predicted an enormous range of independent observations for the better part of a century, 4 explanations. 4 different universes, in a sense, because whichever one turns out to be right will hand us a subtly, or not so subtly, different picture of how everything came to be. Here's what I find myself thinking about, turning this mystery over at night. We are a species standing on a single small planet, orbiting an unremarkable star, in an ordinary galaxy among perhaps 2 trillion others. And we've managed to build instruments precise enough to catch a handful of photons that have been in flight since almost the beginning of time, and precise enough to notice when the story those photons tell doesn't quite match the story we expected. That is an almost unreasonable achievement. And yet, the very act of achieving it has revealed how much we still don't understand. Science doesn't advance primarily through the observations that confirm what we already believe. It advances through the ones that refuse to. A well-behaved universe, one that matched every prediction perfectly, would be a universe with nothing left to discover. And there is something almost unsettling and almost thrilling about the fact that a data set as sophisticated as Webb's has managed, within just a couple of years of operation, to hand cosmology one of its most serious challenges in a generation. So which is it? Efficient early star formation, stretching known physics to its limit. Feasting black holes masquerading as mature galaxies, a measurement error still not fully purged from the data, or a fundamentally different cosmic timeline, one in which the universe is not 13. 8 billion years old, but something else entirely. Perhaps, if the boldest proposals hold up, nearly twice that. I said the story would escalate, and it hasn't finished yet. Because in the years since that first batch of universe breaker candidates made headlines, astronomers didn't just move on, they went back for confirmation, using the most rigorous tools available, determined to settle the question of whether these objects were real. Spectroscopy is the gold standard here. Instead of inferring a galaxy's distance from a handful of broad color measurements, which, as I mentioned, can occasionally mislead, spectroscopy breaks a galaxosque light apart into its full rainbow, revealing sharp, unmistakable fingerprints, specific wavelengths where hydrogen and other elements absorb or emit light in patterns that are essentially impossible to fake or misread. When a redshift is confirmed spectroscopically, it's about as solid as evidence gets in observational astronomy. And spectroscopic confirmation is exactly what happened. Through 2023 and into 2024, using Webb's onboard spectrograph, teams of astronomers confirmed, beyond reasonable doubt, a growing catalog of galaxies existing when the universe was under 400 million years old, some under 300 million years old. With one record-setting object confirmed at a point when the universe was barely 290 million years into its existence, less than 2% of its current age. These weren't photometric guesses anymore. These were locked in, rainbow fingerprinted, peer-reviewed distances. And critically, a meaningful fraction of these confirmed early galaxies still showed the puzzling features that started this whole story. More structure, more apparent maturity, and in some cases, more inferred stellar mass than the standard model comfortably predicts for objects that young. The mystery didn't dissolve under closer scrutiny. It survived it. Which, in science, is exactly the kind of result that turns an interesting anomaly into a serious problem the whole field has to reckon with. A few of these objects became famous enough within the small world of observational cosmology to earn their own shorthand names among researchers. Strings of letters and numbers that to the public sound like nothing at all, but that circulated through conference talks and preprint servers the way a breaking news story circulates through a newsroom. One galaxy confirmed spectroscopically at a redshift, indicating we're seeing it as it existed roughly 430 million years after the Big Bang, appeared to already possess a surprisingly settled, rotating disk of stars, a level of internal organization that standard simulations generally expect to take much longer to develop. Another, observed even earlier in cosmic history, showed emission features suggesting an actively growing supermassive black hole already embedded at its center, at a point in the universe's history when even the existence of a normal-sized black hole, let alone a supermassive one, is difficult to explain through ordinary growth processes. Each of these objects individually could be dismissed as an oddball, a statistical fluke in a very large sky. Together, accumulating survey after survey, they started to look like a population with its own internal consistency, which is a much harder thing to wave away at almost the same time on the completely separate front of the Hubble tension. Something similar was happening. Skeptics had long wondered whether the discrepancy between the two expansion rate measurements might come down to some subtle, uncorrected error in the distance ladder method. Perhaps a miscalibration in the brightness of certain stars used as cosmic mile markers. Webb, with its far sharper vision than previous telescopes, was turned toward exactly this problem, re-observing the same calibrating stars that anchor the distance ladder. In an effort to settle the question once and for all, the result reported by the team most closely associated with the distance ladder measurement was not the resolution skeptics were hoping for. Webb's sharper data confirmed the earlier measurements rather than overturning them, reinforcing the higher expansion rate and deepening rather than dissolving the tension with the value inferred from the early universe. One of the most promising, maybe it's just a measurement error. Escape hatches was, for the most part, closed. So now we have two independent anomalies, impossibly early, impossibly massive galaxies on one front, and a stubborn, now Webb-confirmed mismatch in the expansion rate on the other, both surviving their most rigorous stress tests, both still standing after everyone's best attempts to make them go away through more careful measurement. This is the moment in any good mystery where the detective stops treating the clues as separate and starts wondering if they're connected. And to be clear, the honest majority position in cosmology today is still that these are likely two separate puzzles, each probably solvable within the standard framework: efficient early star formation and improved photometric calibration for the galaxies. Some subtle new physics involving dark energy or neutrinos for the Hubble tension, without needing to throw out the 13.8 billion year timeline altogether. Most of the field's most experienced researchers would tell you that betting against a century of accumulated, cross-validated evidence is usually a losing bet, but usually is doing real work in that sentence, because this is also, historically, exactly the kind of moment that has preceded genuine revolutions in physics before. 3. Think about what it must have felt like at the end of the 19th century. 3. When physicists largely believed the fundamental laws of nature were essentially complete, that all that remained was to measure things more precisely. 3. And then came a small number of stubborn anomalies. The strange behavior of light, which refused to obey the velocity addition rules that had worked for everything else. The peculiar way hot glowing objects radiated energy, which classical physics predicted should be infinite and obviously wasn't. Individually, these looked like minor loose ends. Together, over the following 3 decades, they tore apart the foundations of classical physics and gave rise to relativity and quantum mechanics, 2 of the most successful, most rigorously tested theories human beings have ever produced. I'm not telling you that's what's happening here. Nobody knows that yet, and anyone who tells you with confidence that cosmology is about to be overturned is getting ahead of the evidence. But I am telling you that the pattern, precise, respected, decades-old theory, a small number of stubborn, independently confirmed anomalies, competing explanations, none yet dominant, is a pattern worth taking seriously because we've seen where it can lead before. Let me widen on the lens for a moment, because it's easy in the middle of a story like this to get lost in redshifts and megaparsecs and lose sight of just how much is actually riding on the outcome. If it turns out that the standard timeline survives, that efficient early star formation and refined measurement techniques eventually account for the strange galaxies, and some new but comparatively modest physics resolves the Hubble tension, then the 13.8 billion